Hi, it's Mark. I thought today we could talk about weak decay, which is an important process in particle physics that relates to the different quarks and how they change from one to the other. All right, well, this is a busy chart. The central part of this diagram is the weak decay diagram from Wikipedia. And what it's showing is that the quarks, and they're labeled here T for top, C for charm, U for up, D for down, S for strange, B for bottom. It's showing that the quarks can decay from one to another. So, for example, the top is most likely to decay to the bottom. That's shown by the black line. But the top could also decay to the strange or the down. The bottom could decay to the charm, but then the charm could decay to the strange or the down. I mean, you could see all the lines here. Basically, you can always go to a lesser energy particle in this family. And scientists really don't understand why it works this way because they think these quarks, down strange bottom, up charm top, are unique individual particles that are indivisible. They are fundamental particles, which they're not. We're going to use the point potential architecture of nature here to illustrate how this works. What I've done is on the right, I've made 3 copies of the up quark, and the up quark is shown on the bottom. That's the one we perceive as having the lowest energy because we only see the apparent energy, we don't see the shielded energy. Then the middle illustration on the right is going to be the charm, but to get to the charm, we need to drop the outer binary. Of course, once you drop the outer binary, that means that this overall structure is not as stable, and so the lifetime is limited because the core won't be able to support the personality charges out on the axes as shown. The top is where you drop both the outer and the middle binary, and you get to the point where the very highest energy inner binary is exposed, and with it the most mass, because normally that would have been shielded. And the personality charges stay the same as we look through the up, charm, top family. And then if we go on the left, I've shown the down, strange, and bottom progression, but actually I've just shown 3 copies of the down quark for now. The strange would be the same as the down quark, missing just the outer binary. That's why the strange looks more massy, because we're now exposing what was shielded mass, shielded energy, which was shielded by superposition of that outer binary, which has now decayed. And then the bottom is, again, very similar. It's got the same set of personality charges out on the axes, but the outer 2 binaries would have been decayed, therefore leaving only the inner binary. And then the lifetime on these, if you just got one binary, the lifetime is short. The personality charges won't have anything holding them in position, and they'll decay quickly. In a way, I kind of think about this decay chart opposite the way scientists think of it. I think of it as a down quark having some kind of a reaction or impact that causes it to lose its outer binary, which then makes it into a strange quark. And then when that loses its middle binary, then it's a bottom quark. And similarly, on the right-hand side, if the up quark, which has low apparent energy but high shielded energy, if it loses its outer binary, then we're going to get the charm quark, which looks heavier, as you can see in the middle chart. And then if we lose both the outer and the middle binary, then we're exposing the highest energy binary, which is that inner binary that was shielded previously. You know, this is really fascinating stuff. Let me show you some of the other parts. In the top left, I've just shown a generic diagram for a fermion where the white personality charges aren't filled in. So instead, just focus on that central core. That's the Noether core. That comes in 2 varieties, a pro and an anti-Noether core. But the Noether core is the triple binary that's at the center of everything. When you just have triple binaries that are extremely, extremely, extremely high energy, those are what makes space-time, or you might think of it as the Higgs particles or something like that. But space-time is composed of those Noether cores, at extreme density and extreme energy, but just shielded by superposition. So they're virtually non-interacting. And the reason that's important is because in this weak decay diagram in the center, scientists have shown that as a quark changes from the right to the left or the left to the right, there's emission of a W boson. And the charge depends on which direction you're going. From what I can tell, W bosons are really kind of an ephemeral particle. Say if the top was going to decay to the bottom on that top black line, what would really be happening here is the top would be exposed and then it would interact with the binaries of spacetime, the nested, triply nested Noether core binaries of spacetime. So this exposed top would interact with those. There would be this interaction, which is like the exchange of the W particle, the W boson, and then flying out of that, you're going to lose some energy, but you'll have enough to make the bottom quark. You know, we have provenance, so we'll have to eventually show exactly which point potentials fly through this reaction and end up where, but you can see that you're going to have some exchange of personality charges in this reaction. Now, you're going to go to a lower energy bottom quark, lower exposed energy, but that bottom also just has one binary. You know, as we look at this, we kind of have to consider that a raw single binary bottom or top is extremely highly reactive, right? It's just an exposed single binary at such high energy that it's going to want to react. It will react with spacetime. And it turns out somehow it ends up flipping the personality back and forth from left to right in this diagram. So that's how I think it works. I've also shown kind of a picture of the W boson here in the center of the diagram, kind of as an ephemeral thing. Remember, it's like the point charges in motion from the first particle, like say top was decaying to bottom. It's showing you both, the W bosons are kind of like an intermediate product of all the point charges in the top, plus some point potentials from space-time ether are exchanging somehow and creating the bottom quark. And then likewise, the bottom could decay to the charm or the up quark. So this is basically how it works. And next, I'm just going to turn on the animation so you can kind of watch these different quarks and the Noether core move around. The animation is very primitive. I'm just kind of showing that there's rotating things, the binaries are orbiting, and that the personality charges are probably moving around in the poles. But in reality, this thing would be precessing so incredibly fast that it would just be a blur. All right. Well, enjoy that playing out, and catch you next time.